stage, and we're excited to hear from you this morning. I hope everyone is ready. Um, okay,
Awesome.
I'll start with a bit of introduction. So, Sampaya Bokeh, she's an assistant professor from Polytechnique Montreal in Canada, and I'm very excited to bring her on stage because I'm Canadian. And yeah, she'll be sharing on the topic additive manufacturing for adaptive structures as well. And Sampaya, whenever you're ready, please take it away.
Okay, begin to share my screen and I'll show the entire screen because I have videos. Okay. And Eddie, can you confirm that you see like my full screen of the presentation?
Yes, I can.
Okay. Good afternoon, everyone in the East Coast, and hello to everyone on the wherever you are. So I'm going to talk about additive manufacturing of adaptive structures. I will explain what I mean by adaptive structures in my coming slides. And just to also present to the people who are joining in from Montreal area, me and Shivani, we are the co-ambassadors for the Montreal chapter. We just started it this year, sorry, in 2022, so last year. And we have a good response so far, and we are wanting to connect to people who are interested in 3D printing. So just contact us or come to our next event, and we'll be happy to talk to you all. So just a little bit about what we do in our lab. This is pretty much summarized in the slide here. We do work on like multi-material additive manufacturing. That is because you will see in the coming slides that the adaptive structures are two-part. There is something that is going to adapt the structure or change its shape, and then there is a structure, so you need to have two different materials. And the different kinds of multi-material additive manufacturing that we do in our lab are, first is co-extrusion. Here in this case, I'll talk about this work that I did during my PhD, where a piezoelectric material is co-extruded with a silver ink to form embedded piezoelectric sensors on top of any kind of structures. Then there has this stereolithographic printing that you know is normally restricted to a single material because it's a liquid bath. And here we worked on ways to tailor the degree of cross-linking of the resin in order to have different mechanical properties. So we can have different mechanical properties across the structure and achieve this multi-material effect with a single material. And then I will also talk about today the continuous fiber direct write. In this case, we use shape memory alloys and we embed them into structural materials. Coming from the last talk about 3D printing shape memory alloys, we don't exactly 3D print them. We buy the wires and we integrate them. But we would love to talk to Ashley maybe during the networking session about 3D printing the SMAs as well. And here the fourth one is multifunctional materials. So we designed nanocomposites which can actuate and sense the amount of actuation in the same time. And this is a single material structure, but with multiple functionalities. And then at the end, this is our recent work where we try to use non-smart materials for a bistable actuation. I will also talk about this one today. So I will be talking more about co-extrusion direct write, continuous fiber direct write, and multi-material FFF this in the next few minutes. So as I promised, I would like to explain what is adaptation. So in nature, if you know birds, they have the ability to adapt the size of the wing, the shape, the orientation of the wing while they are taking off or cruising or descending. And this gives them a lot of efficiency in terms of flight. So we wanted to use and mimic this technique, and this is being done by a lot of companies at this point. I would like to share this video from Albatross 1 from Airbus. If you can see here, there are hinges in the wings that help them to change the total span of the wing during the flight. So when they are cruising, you see the wings are all deployed. And then when they land, they don't need that amount of wingspan. So the wings just can fold, and you can have like the space for taxiing or parking the aircraft. So that is what we are trying to look at this point. And now, just to go in a bit detail, what do we need for adaptation? So you need a sensor that can sense a physical change that tells you that, oh, okay, you need to adapt now. And then you need an actuator in order to make the shape change for the adaptation. And this actuator can work from electric, magnetic, thermal, or even mechanical inputs. And then you need a whole control system to say or to make sure that you're adapting to exactly the amount that you wanted. So if you wanted to bend by 90 degrees, you're actually bending by 90 degrees and not at 45. So these are the three basic ingredients that you need for adaptation. In general, I think you might have noticed when the plane lands, all these actuators on the right-hand side, these work mostly by hydraulics and can only do like one single direction motion. And this makes them pretty heavy. They occupy a lot of space, as you can see. And then because of this, they are limited in the scope of the design of the structure itself. So what we are trying to do is we want to make them lighter. We want to make them more compact, and we want to increase the design space. And if you want to know why we want to do it, is because the lighter they are, of course, we consume the lesser fuel, and then it's lesser carbon dioxide. So that is how it also is going to help the environment. So how are we going to do this? We want to use smart materials instead of these traditional actuators. So for those who don't know what smart materials are, you can define smart materials as the materials that can change their behavior in a systematic manner to a response to the stimulus for it. But the systematic manner is very important because it shouldn't be random. You need to be able to predict the change that is going to happen. So, for example, piezoelectric materials are smart materials that can give you a certain amount of electric charges when they're stressed or strained, and vice versa. And shape memory materials can change their shapes in terms of like application of heat or light. And then there are more smart materials. Sorry about that. And I won't talk about these in the amount of time. So just to make it quick, why we use smart materials is they're multifunctional. You could use the same material for more than one function. That makes the structure lighter and occupy lesser space and gives you increased design freedom. That is all the aim that we're looking for at this point. So going to co-extrusion direct write of piezoelectric sensors. Again, piezoelectric sensors are those that generate electric charges when they are deformed or when a force or pressure is applied on them. So this is my work from my PhD on direct ink write. So just to give a quick brief for those who were not present for the previous talk, we use an ink of the piezoelectric nanocomposite, and we dissolve it in solvents that can quickly evaporate after the material is deposited. So in this case, the kind of ink that I developed during my PhD was something that does not require any post-processing, so you can use the sensor right after printing. So you can see here, it's a cylindrical sensor, and giving it a 3D shape makes it more sensitive as compared to just a film that was made from the same amount of material. So we had a decently high D31 coefficient. This is close to the commercial PVDF-based sensors that you find on market. And we did have 10 times more voltage output compared to plain 2D films. And we could print them anyhow that we wanted. So in this next step, what we did was we needed electrodes. If you see, it's a very teeny tiny cylinder, and making electrodes on this is very difficult. So you need to apply either silver, or you need to deposit some kind of electrodes, and because it's a complex shape, it's not very easy to deposit or paint electrodes onto it and be sure that it is efficient. So what the next step was to be able to co-extrude at the same time the two materials. So this is just like the multicolor toothpaste that you see. So we have our piezoelectric ink in a syringe, and then we have silver ink on the sides. And we can print these sensors in any kind of shape that we want, on any kind of shape or surface that we want, as well as on, like in plain air, on spanning surfaces as well. And just to show you an application of this, so we 3D printed this sensor directly on top of a FDM printed wing. And you can see here the picture, and this is the piezoelectric material and the silver electrodes. And as you can see, the two electrodes do not touch each other, which is what we really wanted, so that there's not a short circuit. And then we mounted it on an electromagnetic shaker to see if our sensor works. And of course, it does work. So you can see here, when we hit it with a pin, it can detect the mechanical perturbation. And at the same time, it can detect any changes in the flow of air surrounding this wing. So this was a very ready-to-use sensor that we have made, and there's no post-processing required. You can put it onto any surface, you can put it into any surface, and then use the sensor. Then coming back to actuators, the next step. So here I would like to show something about the actuators that we have been using. And here we have been working with shape memory alloys. You just saw a video earlier that these are the alloys that can return to their original shape once you hit the transition temperature. So if you heat them, they're going to go back to their designed shape. And this is what we used. So during my postdoc at HDH Zurich, this was the PhD student I was working with, and he was trying to design these panels that can change their shapes. So what he was doing was he was using shape memory alloys wires into leaf springs that were designed using PEEK. So these are the leaf springs that are printed with PEEK. And the advantage is that when the shape memory alloy contracts, is heated, it contracts. So you have a shape change. And then when it cools down, the leaf spring brings it back to its original shape. So you have one-way alloy, but you have like a two-way effect upon heating and cooling the structure. But the problem was he was trying to print and do things. So he wanted to have a material that was cheap and lightweight. And so he 3D printed these truss structures with PLA. And then here, because the SMA transition temperature was like 120 degrees and it was higher than the TG of the PLA, we had to use the leaf spring made from a material with a really high TG. So we went for PEEK, and he printed PEEK leaf springs on a different printer, and then he sat down to assemble this whole structure. So although you can have all these amazing shapes. The problem was the design was very complex, and he would take only one whole day to just assemble. So this is apart from the time he took to print the entire structure. And of course, because of all these PLA structures in between, it was not load bearing. So we thought, can we print this entire structure in a single printing process? So the problem with going all FFF was that if you see here that if you go about the transition temperature of the SMA while you are integrating the SMA in the structure, you're going to deform it. And we didn't want to do that. So we tried to develop a direct ink write method where we would deposit these shape memory alloys between structural material that was dissolved in a polymer, dissolved in a solvent, which would evaporate after extrusion. And in this way, we could print these structures at room temperature. And here is one of the leaf spring, and there is a SMA that is integrated into it. And the interesting part about it is that now we're not restricted to in-planar structures, but we can also go out of plane and create conformal structures. So that really increases our design freedom. This was something that we were looking for. In comparison to the assembled peak and SMA structures, here we had to go with polycarbonate because we could not dissolve peak. If you see, we did have to go with a smaller SMA wire size because we needed the wire to really bend and not be too stiff to recoil during the printing process. And that's why we had a smaller SMA. But if you see the strain percentage of the two structures that we made, it's quite similar, and we think that we can achieve similar strains with the 3D printed approach. So it was easy to design, it was quick to fabricate, and still we were not yet load bearing. So we're looking for something that can be much stronger. So what we did was we tried to print these SMAs into composite prepregs. And then we cured these prepregs and we ended up getting really strong structures. So here you can see the video of the shape memory alloys, which are embedded into composite prepregs. And of course, we are still working on optimizing and making this even better at this point. But yes, as a proof of concept, this is a very good active composite that we have made. And then just to end it with an interesting topic. So far we have been working with smart materials, and we were thinking that can we achieve these smart properties with the normal 3D printable materials that are off the shelf of the market? So this was the work that we did at Polytechnique Montreal. This is our postdoc, Hamid, who worked with the collaborators, Hamid Berzadeh from McGill and Daniel Theriot at Polytechnique. So what we did was by defining the dimensions of these lattice structures, here we can change the bistable characteristics of the material. So in this case, it's a normal commercial TPU that we bought, and then there is a commercial carbon fiber reinforced nylon. And by varying the size and width of this carbon fiber nylon, we can achieve the bistability or the actuation behavior in the structure. So I would like to show you a little video about that one. So here you can see that this is the structure. It is being deformed externally. And then that was the previous state where it was undeformed. And the second state of the structure is this one, and it's a very stable state, the second deformed state as well. So if we want to go back now to the original state, the only thing would be to go heat the material to its transition temperature, that is 35 degrees Celsius. In this case, the temperature of transition depends again on the thickness of the width of this carbon fiber material and these struts. So you see now we are at 35 degrees Celsius, and our structure is going to go back to its original shape in a bit. So we did achieve actuation in this case using stronger materials, off-the-shelf materials, and we didn't need to go into smart materials. So this was one of the very interesting work that we did here at Polytechnique. So that was just a wrap up of what cool things we do here in the Laboratory for Intelligent Structures at Polytechnique Montreal. And so in a nutshell, we develop techniques to integrate smart materials into structural components. We develop hybrid materials with multiple functionalities, smart material-based nanocomposites, and techniques to optimize for functional integration into transportation, rehabilitation, and sports application. And we're really happy and excited to work with anyone who shares the same interests. And in this way, I would like to thank all the students and all my colleagues and the funding agencies to help us do this research. And this is our team at the Laboratory for Intelligent Structures at Polytechnique. And with this, I would like to thank you, and I'm open for questions. So
thank you, Sampato, for that. I will start with a few questions that we already have in the question box. The first question, Sampato, have you investigated the hysteresis of the Tamale bistable actuators?
not yet.
Okay.
That's something we're trying to do, but we haven't got there yet. Yes.
All right. There's another question from Jenny Fresh. Is asking, what kind of dynamic or fatigue characterization do you use to understand your SMEs or smart materials?
So, like it was also shared in the previous presentation, we do tests on the DMA to study the mechanical properties of these shape memory-based materials. And we also do the DSC to study the transition temperatures of these materials.
Okay. And the last one, thank you for your presentation. To actuate SMAs, we need to induce strain. Could you please explain how do you induce strain during additive manufacturing?
I think that was for the previous one, that question, because we don't manufacture the SMAs in our case. These are the wires that we buy, and they're already programmed. So we don't induce any strain at this
In
point.
this case. Okay. Well, thank you. Thank you for sharing with us today. And yeah, we'll let you go. Please stay around with us. We will probably be done in about 40 minutes. If you have more questions or you want to learn a bit about our work, please stay tuned so that you can help us out. Thank you.
Thank you, Eddie. Thank you, everyone.